Hi, welcome to astronomy. Hey, let's talk about a few highlights of the solar system. I think it's interesting how we have defined our units of time based on things that happened out in space. So a day is defined as the time it takes for Earth to spin once on its axis. The time it takes for the moon to go once around the Earth is defined to be a month. And then the time it takes for the Earth to go around the sun is defined to be a year. The appearance of the moon are called phases of the moon, and it turns out that the phases of the moon are determined by our viewing point from Earth. So if you think about going into outer space and looking down on the Earth and the moon, the sun will be way over here to the right, so the sunlight's coming in, and the sun's going to shine the moon. So when the moon is on the side opposite the Earth, then we can see the fully lit moon, and it appears to be a full moon. But when the moon is off to the side, well, we can see half the moon lit up by the sun, but we can also see half the moon that's in shadow. And of course, when the moon is between the Earth and the sun, then we only see the side of the moon that's not lit up by the sun. It's kind of interesting. The moon spins on its axis at the same rate that the moon orbits the Earth. And the consequence of that is that only one side of the moon faces the Earth. It's the same side throughout its path around the Earth. So here's the side that faces us, the near side. But there's a side of the moon that's never seen from Earth. And so these images were taken, I think, by the Apollo crew and maybe other space probes that have gone around to the back side of the moon. So how come? Is it just coincidence that the moon spins at the same rate it goes around the Earth? And the answer is no, it's not coincidence. So if you think about the moon as slightly egg-shaped, so this picture is really exaggerating the shape of the moon. It's not this oblong blob. It's more spherical. It's slightly egg-shaped. And it turns out that the close side of the moon is going to experience stronger gravitational force than the far side of the moon, right? Because gravity depends upon the square of the distance between them, the two objects. So the closer portion of the moon is going to feel a stronger force, and that's going to straighten out the moon, pull it forward. And that's what's going to happen down here. It's going to pull the moon forward and help keep the moon facing the same direction towards Earth as it travels around the Earth. Okay, what makes up a lunar eclipse? Well, the lunar eclipse is caused by the Earth blocking the sunlight from the moon. So when the moon travels behind the Earth, it passes through the Earth's shadow, and then the sunlight won't shine on it, even though it's supposed to be a full moon. And it turns out we don't get a lunar eclipse very often because the moon's orbit is not in the same plane as the Earth's orbit around the sun. So it's about 5-degree difference. And so it's not very often that the sun, the Earth, and the moon are all lined up. Most of the time when the moon is behind the Earth, it's above or below, so it actually doesn't pass into the Earth's shadow. Okay, what about a solar eclipse? Well, that's when the moon passes between the sun and the Earth, and the moon's shadow is cast on the Earth. And so for a small region of Earth, the moon will fully block out the sun, and it'll be dark. Now again, because of that 5% tilt of the moon's orbit, the moon doesn't line up very often in between the sun and the Earth. Okay, let's talk about the sun now. Well, the sun gets its energy from nuclear fusion. And it turns out the sun is just so huge, it has a huge amount of mass that creates a lot of gravity. And that gravity is sufficient to squeeze these atoms together so that they get one nucleus. So we take two hydrogen atoms, push them together, so all the protons and neutrons form one nucleus, a helium nucleus, and then a whole bunch of energy comes out. And that's what powers the sun. Now, the gravity is only strong enough to do fusion at the core, the center of the sun. So the fusion happens down there, the heat energy, the light, all that energy is released and travels through the sun to its surface. And it warms up the gases at the surface until they glow. The heating of the surface is not even, so there will be cooler spots that we see as sunspots. Regions that are not showing a sunspot are glowing very hot. They're very bright. And regions that are not as bright, well, they're dimmer, and then we see them as sunspots. Okay, let's move on to the planets. I had to do a little bit of searching on the internet, so I found one where the planets and the sun were fairly drawn the scale. And here's a pretty good one. The sun is one of the most massive objects in our solar system. Most of the mass of the solar system is bound up in the sun. If you could get all the planets this close to the sun, this is how they would line up. The Earth is only about this size. So here's the size of the Earth. If you get 11 of them all lined up here, those stretch across to Jupiter. Yeah, Mercury's pretty darn small. And what scientists have done is they've said, let's break up the planets into two groups. We got the terrestrial planets. These are the ones that are very rocky. They're also the ones that are closest to the sun. So they're called the inner planets. And then we have the other four, which are huge. Those are the Jovian planets, and they're largely composed of gas. They're farther away, so they're called the outer planets. Now you might be wondering, where's Pluto? Well, a few years ago, Pluto was downgraded to the status of a dwarf planet. And it happens to be smaller than the Earth's moon, and that's one of those criteria for defining it as a dwarf planet, not as one of the Jovian planets or a terrestrial planet. Okay, let's hit a few highlights of our planets, starting with the terrestrial planets, or the inner planets. So Mercury is the closest to the sun. Being the closest, it's going to orbit the sun the quickest, 88 days to do that. In terms of size, it's just a little bit larger than the moon. So like the moon, there's very little atmosphere. Mercury and the moon both do not have enough mass to create enough gravity to hold gases to their surface. So any gases that would have been on the surface, they can overcome gravity and just escape into outer space. Now Mercury, being really close to the sun, is also experiencing these tidal forces that slow its rotation so it can match the orbit. That is, one side of Mercury is almost always facing the sun, but not quite. It turns out that Mercury will spin 3 times every 2 trips around the sun. And so there'll be one side of Mercury that's facing the sun a long time, and it's really close. And furthermore, because it has no atmosphere, the temperatures are really extreme. On the sunlit side, the temperature can reach 430 degrees Celsius, but on the dark side, it can be as cold as negative 170. Okay, Venus is the second planet from the sun. It's about the size of the Earth. And of all the planets, it's the only one that's rotating in a different direction. It spins clockwise. So if this is the North Pole and that's the South Pole, and if you look down from outer space onto the North Pole, Venus will be rotating in a clockwise sense. All the other planets, including Earth, rotate counterclockwise. That's a little different. It's a very cloudy planet. The atmosphere is mostly carbon dioxide, and carbon dioxide is a greenhouse gas, which means that visible light from the sun goes through the clouds of Venus, strikes the surface, warms up the surface, and then the surface starts glowing in the infrared. Infrared light then is emitted from the surface, tries to make its way out of the planet, but then the carbon dioxide will absorb it and will glow infrared light back to the surface and keep it warming up. And so it turns out that even though Venus is farther from the sun, it's actually hotter than Mercury, and Mercury's closer. So the surface temperatures are around 470 compared to 430 for Mercury. And that's due to the greenhouse effect and all that carbon dioxide in Venus's atmosphere. Okay, moving on to the red planet, Mars. It's about half the size of Earth. It has polar ice caps, so there's a lot of water up here. The southern pole also has a frozen region, but it's mainly dry ice, frozen carbon dioxide. It has a thin atmosphere, and so that helps regulate the temperatures. They swing between negative 130 and 30 degrees. And Mars has 2 moons. Oh, and I forgot to mention, Mercury and Venus have no moons. Okay, that takes care of the terrestrial planets. Farther out are the Jovian planets, the gas planets. So these planets are formed mainly of helium and hydrogen, just like the sun. Now, if they had enough gravity, they could push these hydrogen atoms together and cause nuclear fusion and start lighting up like a sun. But they don't have enough gravity. They can't squeeze the hydrogen atoms together to do nuclear fusion. Okay, like I said before, Jupiter is about 11 times the size of Earth. Well, 11 times the diameter, right? If you want to look at volume, it's like over 1,000 times bigger than the Earth. It spins very quickly, about 10 hours, so a day on Jupiter is much shorter than a day on Earth. And these swirling patterns, those are the gases. We got the giant red spot here. It's been a storm. It's been happening for over, 300 years, 400 years. And Galileo was looking with a telescope at Jupiter and saw that red spot. Saturn is the second largest planet. It's pretty close in size to Jupiter and spins very quickly just like Jupiter. Has a lot of moons, and you can see 4 of them right here in the picture. And of course, Saturn's main feature is its ring. The ring is composed of ice and rock, and it's thought that maybe a moon broke up, maybe through tidal forces, and the remnants of the moon created the rings of Saturn. Or maybe it was just stuff, particles found in space that Saturn captured, created the ring. Uranus is about 4 times the size of Earth, and its feature is that it spins on its side. So if the North Pole is over here, it's spinning in this direction, kind of on its side. That's unique of all the planets. Now it's pretty far from the Sun, and it has less hydrogen and helium than Jupiter and Saturn. It's referred to as an ice giant. Most of the planet's mass is made up of water, methane and ammonia. It also has some hydrogen and helium. Neptune is the last of the Jovian planets. It's similar in size to Uranus, also an ice giant. It spins normally. The North Pole is tilted a little bit, just like Earth's north and south pole. It's got about 13 moons. And that's the other thing I forgot to mention. All the Jovian planets, Jupiter, Saturn, Uranus, Neptune, they have lots and lots of moons. Okay, what about Pluto? Well, the astronomers got together and decided that they needed a new category for the planets. Pluto was just an oddball. It's smaller than the moon, so down here you can see the moon is right here. It's the largest of these dwarf planets. It doesn't clear out its orbital path, so there's still a lot of rocks and ice and other things in the orbit of Pluto, and that's because it doesn't have enough gravity to kind of wipe those things out or collect them or clear its path as it travels around the Sun. And that was the main idea, or the main criteria, of why it's been demoted to a dwarf planet. And it kind of makes more sense to call Pluto a dwarf planet because there are other objects in the solar system bigger than Pluto that we're also not calling regular planets. We also classify as dwarf planets. So here's a couple of more features of our solar system that we didn't talk about yet. The asteroid belt. It's a collection of rocks and smaller, tinier planets, I guess you could call them. There's a bunch of them between the orbits of Mars and Jupiter called the asteroid belt. And then farther out there's another region of all these small particles. And they're found in the Kuiper belt. And that's close to where Pluto is. And finally there's a few more things we should talk about, like comets and meteors. Okay, comets are large objects. They contain dust and ice and rock, and they follow an elliptical orbit around the Sun. And when they're farther away from the Sun, way out here, well, temperatures are really severe, very cold, and they don't glow like we customly think of a comet. They're too cold to do anything. It's just an object traveling through space. But as it approaches the Sun, it'll be warmed by the Sun. And then the ice will melt, turn to gas, and be ejected off of the Sun. And the particles on the comet also too get knocked out into space by the intense heat, but also something called the solar wind. So the Sun not only emits sunlight, but also emits gases that create the solar wind. And these gas particles that are flying off of the Sun strike the comet and knock dust off behind it to create its tail. And so the comet's tail is always opposite the side of the Sun. Okay, how about meteors and meteorites? Well, I found this neat picture of a meteorite on Mars. So a meteor is like a tiny object from space, and I say tiny in terms of, compared to a planet or the moon. This one's pretty big, the size of a basketball. And that's the part of the meteor that survived its travel through the atmosphere of Mars. So a meteor is something that's falling to a planet, And once it strikes a planet, it'll be called a meteorite. And meteors are often called shooting stars because as they fall through a planet's atmosphere, there's a lot of friction. And the friction is going to heat up the atmosphere and cause it to glow. And it's actually going to shed a lot of material as it melts and stuff boils off of its surface. So they're going to shrink and they'll leave a lot of particles in its path. If it's large enough, there's a big chunk that can actually strike the Earth, make a little crater, do some damage. Okay, if you're interested, you can go back over this video and pause it and read some of the other interesting things I got written up on these slides. Otherwise, I'll see you in class.